So hi everyone, in this video we are going to talk about the decomposition group. You'll see exactly what that is, and we are going to prove one quite technical lemma or theorem that tells us that in a normal function field extension, the residue fields are always normal. Okay, so we are talking about this part, the decomposition group. So again, let G be the automorphism group of F over E, where we think of F over L as E over K, a finite normal extension. And little p is going to be, as before, a prime divisor lying below capital P. Now, the stabilizer of capital P, in this context, it's called the decomposition group, and it is the set or subgroup of all group elements in G that fixes capital P. Right, that's the general name for that is the stabilizer of this little element, of this particular element that the group acts on. But in this context, it's called the decomposition group. So the decomposition group of a particular element, capital B, is exactly those prime divisors. Sorry, those elements that it sends into itself and not to any other prime divisor. Okay. And since we proved that G acts transitively on the prime divisors lying above little p, we know that R, which just denotes the orbit of the number of elements you can reach. So the orbit of P under G is precisely the number of prime divisor of FL lying over P, right? Because if you fix if you have a little p and you consider some capital P above it, and you look at its orbit, right? So you apply any sigma that you can, and get somewhere. Maybe potentially you can maybe using two sigmas get to the same place, but you get somewhere. So the number of places that you get, the orbit, because of the transitivity of the action, the orbit is precisely what we usually denote by R, the number of prime divisors lying above this little p. And by the orbit stabilizer theorem, we know that we can relate R, namely the number of prime divisor lying above little p, with the index of the decomposition group, the stabilizer, of any particular capital P, but this particular capital P in G. Right, so for example, if you want to know how many prime divisors lie above one prime divisor, little p, then you can pick any prime divisor above it and ask what's the size of the stabilizer or decomposition group of that particular capital P. Okay, so we'll get back to this decomposition group quite a lot in the coming lectures, but the first thing I want to do is to prove a theorem which seems to have nothing to do with the decomposition group, but its proof does use the decomposition group. And the theorem by itself is actually kind of meaningless for us because it tells us something that in our context is obvious, but the proof of that theorem is crucial for the rest of the proofs of some of the other results that we do need. So we do need to see the proof. And the theorem is as follows. It tells you that, maybe say you have F over L is an extension of E over K, and I'm considering again a capital P above little p, then if F over E is normal and finite, then what I'm saying here in this theorem is that the extension of the residue fields, the corresponding residue fields, F sub capital P over E sub P, is also normal and finite. Okay? Now, I'm saying that this is useless in our case as a theorem, not as the proof itself, because in our case, the residue fields that we'll start with are going to be finite, like F5 or something, or whatever, or any finite extension of the ground field which we are considering. And all the extensions of them will be finite because we proved already that if F over L is a finite extension of E over K, then that holds also for the residue fields. And we know already that finite extensions of finite fields is always Galois. The Galois group is cyclic. In particular, you are talking about normal extensions. And so I don't need this result, but I need the proof of that result. Okay, and so let's just prove that in this more general form, and but keep in mind that you want to understand the proof more than the statement of the theorem. Now, as I said, we already know that since f over L, the function field f over L extending E over K, since it is finite, because that's my assumption, I already know that this extension is finite. If you remember, we proved that at the very beginning when talking about function field extensions. And I also said at the same time that we know that when f over L is algebraic over E over K, namely when f over E is algebraic, then L over K is algebraic, and also the residue field are algebraic extensions. I didn't prove that, but I said it's the same thing, and that's true. And the reason I'm saying that is because a normal extension is first of all algebraic. So now I want to assume that f over E is normal and prove that the residue field extension is normal. So first of all, I know that because this is algebraic, as it is normal, then this is algebraic, which is a prerequisite for being normal. And so what we are really left to do is really to prove that this thing is normal under these two assumptions. Okay? And to this end, we'll start by proving a little claim. So, we are going to work in the residue fields, but we always want functions because, we can do more things with function than with their evaluations with, elements in the residue field. So when you're going to give me an element here, Z, in the residue field of capital P, I want to kind of encode it or find a representative, like a function y in O capital P that, first of all, its residue, like when you mod y out by m capital P, you get Z. So y corresponds to Z. Like, y at P is Z, that's what I'm saying. But moreover, you wanted to have some other properties. You want to find a function y that not only evaluated at P to be Z, you want something more. And these are the two items that we need. So the first thing I want, what I'm saying in this claim is that for every Z, you can find a representative Y, such that first of all, for any sigma in G, like, any conjugate of Y, if you look at sigma Y, any conjugate of Y, then that will also be defined at P, right? Evaluation is non-negative, means that it is defined. So you can find a representative, you have this particular capital P that you care about, and Z, which is an evaluation output. So what I'm saying is you can find a function in O capital P that not only it is defined at P, but also actually all of its conjugates, okay? And secondly, I want that sigma Y to vanish, not only be defined, but also vanish at capital P, which just says that evaluation is strictly positive, for all the sigmas in G that I can ask that for, right? So, I don't know what Z is. If Z is not in MP, it's like it's not zero in this residue field, then I can't have a representative whose valuation is larger than zero, because for the identity function, for example, when sigma is the identity element, I'll just get VP of Y and it's Z, and I don't know if Z is in MP or not, so I can't require it to be in MP. And the same holds true for any element in the decomposition group, right? Because if you're in the decomposition group, then P is sent to P, right? And so you have like, for every sigma in the decomposition group, we'll have that V, let's see if I can do it without making errors with the sigma inverses. We have that, so I already started wrong. You have this thing, and now I can apply sigma inverse to both things, both to the point and to the function. That's kind of how we define V of a sigma of something. And if sigma is in the decomposition group, then sigma inverse is also in the decomposition group, the subgroup. Maybe I should have said that, but we know that the stabilizer is a subgroup. And right, and then that's V capital P of Y. because it's a decomposition group, it keeps P at the same place. And I can't require this to be positive or anything. It could be 0. I mean, this thing, I don't know what it is. Maybe it's 0, maybe not. I know it's either 0 strictly positive, it's not negative, because I'm taking a representative of Z, it's something in OP, but I can't require it to be strictly positive. But whenever sigma sends P to some other prime divisor, then there is hope, and that claim tells you that you can make sure that sigma y actually vanishes when you're not in DP, okay? For those sigmas. Okay, so let's prove this claim. So we are going to start by taking some representative y prime for Z. Namely, you know that Z is y prime plus AMP. And we are going to kind of massage it so that it will have the requirements that we want, okay? So first of all, know that if you take sigma that is not in the decomposition group of P, then P is not sigma inverse P, right? Because if sigma is not there, then also sigma inverse is not there, or you can just take sigma to the other side. And therefore, by the weak approximation theorem, you'll see where this comes in. By the weak approximation theorem, there exists a y, that's going to be our y, such that, so first of all, y is close to y prime. How close? At least 1 or equal to 1 with respect to P, with evaluation capital P. And secondly, y is close to 0, so you have like y minus 0 here, with respect to every prime divisor that is of the form sigma inverse P, for every sigma that's not in the decomposition group. Now, when you apply the weak approximation theorem, you must make sure that you have finitely many constraints that you wish to occur, and they should not contradict each other. In particular, the best way to do that is to make sure that all of these prime divisors are distinct. And indeed, these are distinct because of what I just said before, right? Because sigma is not on the decomposition group. We know that sigma inverse P is not P. And so this prime divisor is different than that prime divisor. And so these two won't contradict each other. Right, I mean, here you require y to be close to y prime, and here you require y to be close to 0. And if it was with respect to the same prime divisor, maybe you cannot do that because maybe y prime is very far from 0, and you can't find a y that's close to two things that are far apart from each other. Okay, so it's good that you're considering different matrices or different valuations, and they are independent. That's what the approximation theorem is all about. So you can require those things. Now, we know that v capital P of y prime is at least 0 because y prime is in OP, it's a representative for this z, and we know that y is close to y prime, or y prime is close to y. In this case, for that particular line, I only need a larger or equal, by the way. And so because this is larger or equal than 0 and this is larger or equal than 0, then we know that also Vp of y is larger or equal than 0. Right? That's the usual trick of saying that valuation y is at least the minimum between the valuation at y prime and the valuation at y minus y prime, because these two sum up to y. And since both of them are at least 0, we know that also y has valuation at least 0, namely y is in OP. Okay, that's a good start. I mean, we want more than that here, but yeah, that's the good start. You know that there is a representative y in OP, so at least the y that I'm claiming that we are going to end up with is in OP. But we still need to show all of these and also show that it's a representative, by the way. So now this item 2, actually implies item 2 here. Just looks different, but it's the same thing. Because item 2 here, if you stare at it for a second, it tells you that for every sigma that is in G but not in the decomposition group, which is the same requirement here, now it iterates over the same sigmas. What's written here is that V sigma inverse of By is at least 0, but you can apply sigma to both and you'll get that Vp of sigma y is at least 0, like it's larger than 0. That's the same thing, right? These two are equivalent, and this is what's written here. I mean, the reason I wrote it like that is so that we can see that we are, like, I don't like to apply the weak approximation theorem of sigma of y. So I want to find a y such that. So I wanted the y to be written here without applying some automorphism on it. And I moved the automorphism here, which also allowed us to see that we are working with different primes. But then when I want to cache out and actually prove the result, it's stated in this form. So yeah, that's a better way of looking at it as a part of the claim statement rather than part of the proof. Okay, but two we have. In this part we have. And now let's check that item one holds. Okay, that for every sigma in GVP of sigma y is at least 0, including 0 potentially. So, okay. So actually for sigma that is in G and not in DP, we know that. I mean, for sigma which is not in the decomposition group, we actually have a strict inequality. So all we are left with is handling those sigmas that are in the decomposition group, right? So you take some sigma in the decomposition group, and then, okay, so we want to evaluate that thing. So VP of sigma y is, as before, I'm applying sigma inverse to both the prime divisor and the function. So it's V sigma inverse P of y. And because sigma and therefore sigma inverse is in the decomposition group, we know that this is just capital P. And that is at least 0, right? Because of somewhere that it's at the very beginning somewhere. I can't seem to spot it right now. Yeah, this one, yeah, here. Right, so we have everything in place. I mean, we know that also. The only thing we actually haven't checked is that y is indeed a representative. I mean, you took y prime, which is a representative, and then you cooked up a y that has all the requirements, but maybe it doesn't represent z anymore. But it does, because we made sure that it will be very close to y prime, and indeed, if you notice carefully, we didn't use so far the strict inequality, only the non-strict inequality. But the strict inequality will finish the proof because, right, you know that, and so you know that y plus mp is y prime plus mp, right? Because like saying that the valuation of some function, in particular the difference between these two, is at least 0, it means, in terms of places, it means that y minus y prime vanishes at p, it's 0 at p. But in terms of valuation rings and the ideal, corresponding ideal, it means the y minus y prime is in MP. Right, their difference is like 0 in the residue field. When you mode out by MP, which is how you go from the valuation ring to the residue field, you get 0. And that's the same thing as saying this. And this is Z. I mean, right, this whole thing is Z, because y prime was initially a representative for Z. Yeah, good. So that's the proof. It's slightly technical, but it tells us at the end of the day that if you start with an element in the residue field, you can always kind of lift it to a function in the corresponding valuation ring. I mean, there is a function that when you evaluate it at P, you'll get Z, but that function behaves nicely on the prime divisors that are kind of associated or kind of conjugated with capital P. Okay, so they are usually, I mean, whenever they can, so this y, whenever you can, sigma of y vanishes at the primary ideals above little p, and when you cannot, then it's at least defined, larger or equal than 0. Okay, so with this, let's prove the theorem that we have here. So as I promised, it's kind of technical, but okay. So, we want to prove theorem 16. Let's remind ourselves, we want to prove that this is a normal extension. So, what would you do? You use one of the, your favorite kind of characteristic or property or way of defining normality. So, but what we are going to do is essentially going to the origins, the original definition, and we are going to take Z in FP and show that all of its conjugates over EP are also in FP. Okay? Namely, if you look at Z here, and you look at its irreducible polynomial, then like over AP, it's minimal polynomial over EP, then all of the roots there are in FP. Okay, once you have a root, all roots are there. Like when U is the minimal polynomial of this element in FP. Now, what we are not going to do is to take Z and consider its minimal polynomial. That's not what's gonna happen because we will have less control of this minimal polynomial. Instead, what the proof strategy is the following. We are going to take the element here, and we're going to consider a polynomial. It's going to take us a little bit of time to construct it, that we will show all of its roots, Z is one of its roots, and all of its other roots are also in FP. And therefore, because Z is its root, then it means that the minimal polynomial of Z must divide that weird polynomial that we constructed. And since all the roots of this weird polynomial are in FP, then definitely all the roots of the minimal polynomial of Z, which is just a factor of that polynomial as a polynomial in EP. All of these roots are also there, right? So that's what we're going to seemingly prove something stronger, but actually it's easier to do it. Like, at least I don't know how to do it in a more straightforward fashion. Okay, but let's do it slowly. So we're going to take Z in FP, and we're going to show that all of its EP conjugates are in FP. And we are going to take a Y, dy, that is the nice representative, or not dy, but a Y that is a nice representative as promised, as we showed exist by claim 17. And don't worry about what nice means. We'll get back to it when we need it, but Y is a nice representative, okay? And now what I'm going to do is to consider the following polynomial. That's not the polynomial I promised you, but that's the start. So I'm going to define f of x, f of capital X, like symbol capital X, to be the following. So I'm going over all sigmas in G, okay? And for each of them, I have the following factor. So I'm looking at x minus sigma y. So sigma acts on y. I'm taking this thing to the power q, where q is the extension of f over es, if you remember. So this is a degree q extension. Okay? And we know that everything here to the power q is pulled back down to here. Okay, so this is a polynomial. You can also write it like that, by the way. I mean, you can push the q, because we said that q it was part of the theorem. Q is a power of the characteristic of all of the fields that are involved. Then you can push it here inside, a minus b to the q is a to the q minus b to the q. And you can also push q, that will give you x to the q minus sigma y to the q. But then you can push q also within sigma, like we have here, because sigma is multiplicative. And so anyhow, what I'm saying is that this equality holds. Okay? And the weakest thing I can say about where little f of x lives is in capital F of x, right? Because y is an element in F, and therefore sigma y is an element in F, and therefore when you open it up, all the action happens in the field F, and so the coefficients of these polynomials are in F. Right? We are going to show much more in that, but at least at this point, the coefficients are in capital F. But in fact, if you think about it for a second, you can say something stronger, because you know that y is in OP. That's how you chose y initially even. But you know that actually sigma y is in OP for every sigma in G. That's claim 17. That's item 1 in claim 17. Right? It tells you that sigma y is in OP. This is stated here in terms of valuation, but sigma y is in OP for every sigma in G. So this is not just an element in F, it's actually an element in OP, or capital P, and that's a ring. So again, when you open this up and see what you get, the coefficients are just like polynomials, really the symmetric polynomials and the powers q's and so forth, but some polynomials in elements in OP, and so there are also elements in OP. So in fact, this polynomial has coefficients in O capital P. Okay, so far we said that we placed f in, forget about f of x, in O capital P of x. But now I want to do something more, or I don't know, orthogonal to that, and then combine the two. So if you look at this expression, not at this one, it's easier to see it from this expression. We know that y is in f, so it's somewhere here. And therefore y to the q, as I said, it's an element in ES. So this is an element in ES. And what I'm claiming, therefore, is that also sigma of yk is in ES. Right. So since y to the q is in ES, we know that this element is separable. And sigma is an automorphism of f over E. So this thing, for every sigma, is some conjugate of y to the q. Now, what's a conjugate? It's one of the roots of the minimal polynomial of yq. And therefore, it's also separable, right? Because the fact that yq is separable means that in the minimal polynomial of y to the power q, you have no repeated roots. And now the other roots there are sigma of this y to the q. And sigma of y to the q also has this same minimal polynomial. And also, it's the same polynomial. It still doesn't have repeated roots. So anyhow, what I'm saying is that all of these elements, conjugates of separable elements, are separable elements. So this thing is also in ES. And this means that f actually also lies, so the coefficients of f are also in ES, right? Because you have these separable elements here, and the ES is a field, so when you take sums and products of elements there, you still get element there. And so f lives in O capital P from different reasons, by the choice of y, but because y to the q is in ES, it also lives in ES. Okay, and why am I saying that? Because now observe that if you apply any tau in G to f, like to the coefficients of f, when you apply tau, you mean an action, if you have an action on, if you have an action on some field and you look at the polynomial ring over that field, then the action extends to the polynomial ring by just acting on the coefficients of the polynomial. Right? So if you apply, if you let tau, any tau in G, act on f of x, and maybe it's easier to see it from here or from here, I don't know, the same thing, then you see that nothing changes, because when you apply, for example, here, this is easier. When you apply tau here, you get, the tau is applied to the product, and tau is a multiplicative, so you can push it inside, and then, as I said, it doesn't affect the q, only this thing, so it's essentially that. But then, iterating over all sigmas and taking tau sigma, or just iterating over sigmas without taking tau sigma, it's the same thing, because you're doing something symmetric. You're just taking the product. So anyhow, what I'm saying is that the coefficients of f are fixed by any elements of G, they are fixed by G. And so this means that f of x, like the coefficients of f, are in the fixed field of ES by G, which, because this is a Galois extension and G is the corresponding Galois group, it is exactly E. Right? So f is in fact a polynomial over E. Good. So because of this discussion, we know that f is a polynomial over E, but we know also that it's a polynomial over OP. And so it's a polynomial, the coefficient of f of x are in E and in O capital P, which is precisely O little p. So all in all, we proved that f actually is not just a polynomial in f, it's in capital F over capital F, it's a polynomial over capital over O of small p. Okay. Okay, so to summarize, so far we proved this thing. We proved that this polynomial, which is not the polynomial I promised you, still, is a polynomial with coefficients in O capital P. And so this means that we can mod out the coefficients by MP, right? So we can kind of, like, the coefficients are actually functions that are defined in small p. So we can evaluate them at small p, or mod out by MP. So, I'm going to do that, but I'm going to do also something else. So recall that for sigma that is not in the decomposition group, by claim 17, we have that V capital P of sigma y is strictly larger than 0. Right, that was the second item that we haven't used so far. what does it mean? It means that if you take sigma y plus mp, or I'm going to use also this notation, like as a bar, as saying that I'm modding out by the corresponding maximal ideal, then that's 0, right? So in the residue field, sigma y for sigmas that are not in the decomposition group just vanish, just 0. And therefore, if I do what I promised and considering this polynomial, but I reduce it modulo p, but not little p, actually modulo capital P, I can also do that, of course, because it's also an O capital P, because it's just a subset of that, subring of that. Then, and I call this thing f bar of x, when I get something whose coefficients are in the residue field corresponding to capital P, of course. And what is it? So f bar of x is, well, I'm just kind of barring everything here. And bar, like modding by MP, it's a multiplicative, it's like an isomorphism. So you can go from this to this. It's multiplicative, and also through the Q, and it doesn't affect x, of course. X is a symbol, and so you put it here. Okay. So f bar x, you can either bar the coefficients or bar the roots, because it's the same thing. So you have this thing, and now because of what you just said, when sigma is not in the decomposition group, this thing goes away, right? Because it's 0, and so you'll get just x to the q, and the number of times you get x to the q is exactly how many elements in the group you have that are not in the decomposition group. So this is this factor that we factor out of this polynomial. And then the rest of the elements here are, you go over all sigmas in the decomposition group, and you just copy this thing here. Right, and recall that we said, regardless of any of that, that's also in EP of x. Right? I mean, the original polynomial was in EP of x. Definitely, when you mod out by something, it's still in EP of x. Okay? So we conclude that this polynomial, and that's the polynomial I promised you, right? It's this thing here, is also in EP of x, right? Because I know that this times that it's in EP of x, but I can always just remove this factor, and I'm still left with a polynomial that's over the same field. And the point is that this polynomial has all of its roots in f capital P, because we know that sigma y is in OP, right? For every sigma, that's item 1 in the claim. Sigma y is in OP, so this means that this thing is in FP. So this is a polynomial, all of its roots are in FP. And if you consider what happens when you plug in z, then you get 0, right? Because g of z is g of capital Y. Y is the representative for z. And capital Y appears here because when you take sigma to be the identity, which is in the decomposition group, right? If anything is in the decomposition group, it's identity. That's the thing that leaves everything in place. Then it's there. So when you plug z or y bar, you get 0. And so this is it, right? You found a polynomial over EP that vanishes at z, and all of its roots are in FP. And so this means that the minimal polynomial of z over EP, also has this property because it just divides. Maybe it is this polynomial, but it probably just divides this polynomial, mostly because of this q. And so you're done. You found that all the EP conjugates of z actually also lie in FP. So this means that this thing is normal, and we conclude the proof.